Let's look at some application problems of second derivative, the first derivative and the second derivative. The velocity of an object that is s of t units from a starting point. So s is giving us the distance. Let me go ahead and write that down. So s of t, this is the distance function. If you want to know where what did they say? An object, okay. If you want to know the position of an object at time t, then you plug it into s of t, okay? But if you want to know its velocity, okay, its speed to a certain direction, then what you need to do is you need to find the first derivative. Let me highlight these. So anytime you're looking for velocity, find that first derivative, find that rate of change, okay? The acceleration is the second derivative. So if you need to find the acceleration, a of t is the velocity, the derivative of the velocity. In other words, the second derivative of our distance function. So just the two things that I highlighted should be helpful. Let's use those to answer example number 4. Example 4, from the point at which an object is dropped, the distance it falls in t seconds, assuming negligible air resistance, is approximated by, I need to underline or box this function, s of t equals 4.9 t squared. So this is the distance function, okay? So this will give us where this object is. Okay, at time t, where s of t is in meters. Okay, if a stone is dropped from a cliff, find each of the following. Okay, A, how far the stone has traveled 5 seconds after being dropped. Look at the wording. They're simply asking you for the distance, right? How far? So all I'm going to do is I will plug in 5 into my distance function. S of 5 is 4.9 times 5 squared. What is that going to be? 4.9 times 25 is 122.5 meters. Okay, so let's put the units. The unit is going to be important for the velocity and acceleration. So if the wording of the question is simply asking you to find how far, just the distance, I plug it into the s of t. Okay, now what's next? B is asking how fast is it traveling. It's asking for the speed. It's asking for the velocity. So in that case, we're going to have to find the first derivative. How fast is it traveling? They're asking for the velocity. So in order to find the velocity at t, I'm going to find the first derivative of our distance function. So if the distance function is 4.9 t squared, first derivative is, we still use the power rule, remember, we do 2 times 4.5, let me see what that is, that's 4.9, 4.9 times 2 is, I got 9, whoopsie, that's a highlighter, 9.8, and t is getting raised to the first power. So that's the first derivative. So this is the velocity function. So velocity at time 5 is simply 9.8 times 5. Okay, this is how fast it is traveling. So if I multiply 9.8 by 5, I get 49. And let's be careful with the unit, meters per second. That is how fast this particle is traveling at 5 seconds. The last question, of course, has to do with the velocity. Whoopsies, it's acceleration. Is acceleration after it has been falling for 5 seconds? So if you want a of t, the acceleration, remember that is the derivative of the velocity function, which means the second derivative of our original distance function. So I was right here. Let me go ahead and just find the second derivative. S double prime of t is equal to, we use the power rule again. We multiply 1 times 9.8, which is just 9.8. And it's going to be t to the 0th power, right? But what is anything to the 0 power? That is just 1. So guess what? Velocity acceleration is actually constant. It's just 9.8. 9.8. So if they're asking for acceleration at 5 seconds, it doesn't matter what second they are at. The acceleration is always 9.8 meters per second squared. Make sure you put second square for the unit for the acceleration. Okay, so that's it. That is an application problem for first derivative and the second derivative. I think the next one is similar, and since I've been only going for about 6 minutes, how about I do the next thing? Example 5 here, okay? All right, the number of Apple iPads sold per year in millions, t years after 2010 can be approximated by this n of t function. So if you want to know how many iPads are sold in a certain year, all we're going to do is we're going to just plug it into this function. Okay, so this is going to tell us how many iPads are sold. Okay, so what do they want? They said find n of 7. We know how to do that. We're just going to plug in 7 into that given function above. So let me write it down, you guys. Maybe you can plug it in when I write this down. I'm just writing it down, such a long function. But I try to write legibly for those of you who are just going with the note instead of the video. Oh, this is so long. I am out of room. And these were even in millions, right? So, okay. 20.714. And what I'm going to do is I'm just going to go ahead and plug this into my scientific calculator that I'm holding. Skip forward a couple seconds if you just want to see the answer. I'm slowly typing this in. Plus 20.714. I got 68.097. So what does that mean? Because 2010 was like year 0, okay, this is t equals 0. When they say t equals 7, that means 7 years from 2010. That's why they're saying in 2017, Apple sold approximately 68.097 million iPads. Oh, goodness. Okay. So how many is that? 68 million 97,000 iPads. That's a lot of iPads they sold. Okay, but this wasn't too difficult or anything, right? We just had to plug it in, and that's what it was. But you know, in case if I made a typo, please let me know so that I can take this video down. All right, how about n prime of t? Ooh, for this one, we will need to find first the derivative. First, find n prime of t. And then we're going to plug in t equals 7, okay? So what is derivative function for that iPad number function? So let me go ahead and multiply 4 times 0.106. The new leading coefficient is 0.424 t to the 3rd power, right? So we're done with the first term. Whew. Next, I'm multiplying 3 times this number, 3 times 1.452, and this was a subtraction in between, so let me put that minus sign, 4.356 t squared, right? Doing good. All right, next term, I'm multiplying 2 times 5.659. I got plus 11.318 to the times t, because it's just t to the first power. And I think, well, we're almost done. If you differentiate this 1.946t, that's just going to be plus 1.946 with no t. 6 with no t. And lastly, the constant, derivative of this constant will just be 0, so we do not need to write it. So, it took a while. It's just because the numbers were so long. Now let's plug in t equals 7 in here. I'll go ahead and write it down. And guys, I think I got this home a problem from your textbook. So maybe after this lesson, I can go into the textbook to check my arithmetics, because I'm just using my little scientific calculator. Who knows, I have a typo. But I know Vivian and others are watching this for me and gonna let me know if there's anything wrong with this. All right, so I plug this in now, okay? When I plug this in, guys, I got 13.16. What does that mean? In 2017, Apple's yearly sales of iPads were 13. Oh, no. I'm going to go ahead and write the number later. Can you go ahead and write increasing? Their sale was increasing at the rate of about 13.16 million units per year. Why am I saying increasing? This is a positive answer, right? If it was a negative, I would have said their iPad sale is decreasing at this rate. But, their sale is, the rate of change of the number of iPads sold is positive, so their sale is increasing at that number of iPads per year. Okay, doing good. How about the last one, the second derivative? Okay, let's go ahead and find the second derivative of t first, and we will plug in 7 in there. So I'm going to go ahead and look at this line above. I'm going to go ahead and just highlight this temporarily or circle this so that you know where I'm working from. So I'll go ahead and take the derivative of this. I find 3 times that leading coefficient, okay? And that is 0.424 times 3, 1.272, and that's t to the second power, isn't it? That's t to the second power. Let's keep going. Next, I'm multiplying 2 times negative 4.36356. 2 times 4.356. Next term is minus 8.712 t to the first power, right? Because it used to be t squared, now it is t to the first power. Let's keep going. Plus, now if you look at this term, wouldn't that just be 11.318? Because next it will be t to the 0th power. And the number, the constant will just give us 0, so we do not need to put it. We found the second derivative. Let's find n double prime of 7 and explain what that means. So plug in 7 for t. You see, every time we take derivative, we are losing a term that was a constant on our previous derivative, right? So if this one is a little bit shorter, 1.272 minus 8.712 times 7. After this video and after finishing this, I'm going to go and draft your first exam, and I will post something on line for you very soon. I got 11, whoopsie, that's not 11, that is 12. 12.662. So what does the second derivative mean? Because the first derivative meant that their sale is increasing at that speed. So let me read this. It says in 2017, that's t equals 7, the rate of change itself, changing at a rate of 12.662 units per year squared. So this means their sale is accelerating. This is a positive number. So it's a good thing for them. Their sale is increasing at this speed. Okay? Since the rate in the rate of change of the sale is positive, since the second derivative is positive, the sales are accelerating. So this last sentence is really what it means. This iPad, Apple's iPad sales were accelerating in 2007, and that rate of acceleration was 12.662 million iPads per year squared. Now, I may have to change this because weren't these given in millions? So if they didn't really write the million here, I can just squeeze in the word million. If not, I may have to multiply this by 1 million and get 12,662,000 units per year. So they didn't have the million over here, so either you squeeze that millions in or just add 3 more zeros after it, okay? So that's enough, and you know, that's usually where we stop for 1.8. You saw enough. I'm going to come back and do this daily problem example because you will get something a little different. Maybe, who knows, maybe if you're lucky you get the same one that I'm about to do. But I'll do that in another video. And I have a couple other examples, like extra examples or like an extra credit problem type that I'll often put on your first exam. But I'll just make those videos optional. But if you watch those first 3, then you should be good to start on your homework. But if you need a little help on 1.8 daily problem, I'm about to go and do that one right now after this, okay?